And so what this is 3 fatty acids esterified to a glycerol backbone. All right, so how does that work? Well, first of all, let's do the glycerol. So the glycerol is, what's its official name? What, 1,2,3 propane triol, I guess. 3 carbon molecule with 3 alcohols coming off of it. And at each of these alcohol, remember that an ester is the linkage between a fatty acid and an alcohol, and you remove water from in between to make the ester. And so what we're going to do is we're going to have 3 different fatty acids that are going to be esterified to these 3 different alcohol positions. And I'll just go ahead and draw the fatty acids here. And I'll draw them as fatty acids just because it'll make it look neater when we actually do the condensation. And so we'll have this carboxyl group here, and let's see, we'll do this one, let's see, we'll do palmitic acid. We'll start with palmitic. What is that? 16 carbons, no double bonds. So 1, 2, 4, 6, 8, 10, 12, 14, 16. And then we're also going to, at this other position, we'll esterify it to maybe a different fatty acid. Maybe let's see, we'll do oleic acid because I'll kind of give you a hint for drawing oleic acid. A hint is do 4 peaks, 1, 2, 3, 4, the double bond, and then another 4 peaks. And then just for practice, maybe we'll do linoleic acid. So that's going to be the 4 peaks. 3, 4, the double bond, then another peak and the double bond, and that's 12, 13, 14, 15, 16, 17, 18. There we go. Now what we're going to do is remove a water basically from in between that carboxylic acid and the alcohol to create the ester. So essentially we are going to take this out, take this out, take this out, remove those. So that we end up with two, 4, 6, 8, 10, 12, 14, 16. There we go. There is our triacylglycerol. So acyl is referring to the fact that there is an ester and that there's 3 of them. Triacylglycerol. Get the structure of that. I'll kind of give you a hint already. I usually don't tell people exactly what's gonna be on the exam, but I pretty much, every time I do an exam on this, there should be, I gotta post the practice midterm 3. I basically say, draw the structure of a triglyceride. And most people get it right, because a lot of times people get confusion about how, remembering how to draw an ester. So remind yourself how to draw that ester.
I have a question.
Yes.
So each time one of those bonds is formed, the water comes out of all of the bonds?
That's right.
Okay.
So I guess more completely, what I really should do here, say plus 3 H2O. As a net reaction. So if you think about that, that's how we have made a lot of different molecules, right? When we think about making the peptide bond, we took 2 amino acids and we did a condensation reaction where we removed water. When we made our polysaccharides, we took glucose molecules and linked them together with glycosidic linkages by removing water. So there's another variation on that theme. All right, so now what I want to do is I want to differentiate different types of triacylglycerols, sort of structural classes, differentiate fats and oils. Oh my God, I might have to just redo this. So we're going to differentiate between fats and oils. This terminology is a little bit loose, but it's not totally loose. So fats are triacylglycerol trags that are solid at room temperature so which means they have mostly saturated fatty acids. You tend to find them common in animal fats. So animal fats tend to be, so what is, like when my mom, back in the old days, she grew up in West Virginia, had kind of southern cooking. I don't know if anybody's family ever do this. Like she'd fry up bacon. She would keep the bacon grease in a jar on top of the stove, right? And then use that as as a cooking oil, right? And even in the hot Cincinnati weather, it would still be a solid there. It would be this yellowish, whitish solid stuff. So that was pork fat, right? Let's see. Beef fat, did we talk about that? That's tallow. Tallow is beef fat. What are the other names?
Ghee.
What's that?
Ghee.
What?
G-H-E.
So what animal is that from?
Like from a cow.
Oh, that's also from a cow?
Uh-huh.
Okay, very good. How about in Spanish? What are the different names in Spanish? Like what, manteca is one, right? Manteca is, what kind of fat is that? What animal is that from? Anybody know? Anybody from Manteca? If you're from Manteca, you should be able to know that. There's another one. Isn't there another name in Spanish with different fats? Manteca.
Isn't that pork fat as well?
Is Manteca pork fat?
I think so.
All right, we'll have to look this. I have to refresh myself. We'll look this up. Come back tomorrow and we'll get all this down.
Yeah, it's pork fat.
It's pork fat. Manteca is pork fat. What's the Spanish word for beef fat? Do you know? Anybody know that? Anyway, we'll figure that out. Okay, so common in animal fats. Now we're going to differentiate that from oils. So these are tags that are liquid at room temperature. These are mostly unsaturated fatty acids. Okay, common common in plant fats, or common in plants. But I'm going to put it one exception here because it turns out that it's important in food chemistry, except palm. Palm oil is more like an animal fat here. Butter, by the way, is that's an animal fat. It is a little bit different than, say, tallow, in that the fatty acid chains, whether saturated, they tend to be shorter fatty acid chains, like 8 and 10 carbons in there. So it's a little bit of a funky fat. So that's going to be milk fat, right? That's coming from the dairy. I don't know what the actual composition like of human milk fat is. All right, so another little story relating to food technology. So, one of the problems is saturated fats are associated with high cardiovascular risk, basically consumption of that relative to oil. So people recommended, reduce your saturated fat to reduce your cardiovascular risk. But there's some things, so a lot of times things have been substituted, the animal fats have been substituted with the oils, and oil and plant oils tend to be cheaper than animal fats, also in the fat marketplace. So you like to be able to substitute plant oils, but there are certain uses of fats in cooking that are tough to substitute. So one is frying, deep fat frying kind of thing. You like to have a nice saturated fat for that. Another one is baking, cooking like baked goods. That if you try to substitute oil in for your butter, butter is an expensive fat. So if you try to substitute oil for your butter, the mouthfeel and the baking quality just isn't quite right. So a long time ago, to get around that and basically provide a cheap source of fat, because I said the animal fats are relatively expensive, to find a cheap source of fats, there's a technology generated to take soybean oil, which has a lot of unsaturated fatty acids, and convert it to a solid fat. And that was by hydrogenation, catalytic hydrogenation. You just take the triglyceride, say this is soybean oil here, you just take the triglyceride and you add bubble hydrogen gas through it with a little platinum or palladium, and you reduce all these double bonds in here. And so it turns into a saturated fat. And that's essentially what Crisco was. You remember Crisco? They still sell Crisco, but old-fashioned Crisco you took was hydrogenated soybean oil. Now you didn't want to actually fully hydrogenate it because then it would just be too solid. So you only partially hydrogenated. So it was partially hydrogenated soybean oil, partially hydrogenated vegetable oil. And now the problem with that is that when you partially hydrogenate it, some of the side products of the reaction is just isomerize the fat from a cis double bond to a trans double bond. So all those products with partially hydrogenated vegetable oil on had a significant amount of trans fats. Those are fats that actually had the double bonds are trans double bonds. Here's another product that had a lot of that peanut butter. You know your Skippy peanut butter that you have? That nice peanut butter? That Skippy peanut butter, it's not just peanuts ground up. That's that fancy organic stuff, right? But that it's all oily and kind of tough. It's kind of a mess, kind of a little bit of thing, a little bit. So what the food scientists did is they cut some partially hydrogenated fat in there to kind of give it a better spreadability and all that sort of stuff with the trans fats. Well, it turns out from an epidemiological standpoint, trans fats are very risky for cardiovascular risk, more risky than saturated fats. There's something kind of unique about those. And so there was basically an effort beginning about maybe a decade ago, maybe a decade and a half ago, to actually try to eliminate the trans fats from the food supply. Countries outside the U.S. were a little bit quicker. They just would put a ban on it. Whereas the U.S. was a little bit slow, and then they had but then what they did do is they made a labeling requirement that you had to label whether or not your product actually had trans fats in it. And that labeling actually was pretty effective, that the consumers were pretty wary of the trans fats. And once there was a labeling requirement, consumers really avoided those products that had significant amount of trans fats in it. Things like the peanut butter, things like the Crisco oil. Actually, old-fashioned margarine, old-fashioned margarine, that also had partially hydrogenated vegetable oil with a lot of trans fats. So, so the solution, you can still buy Skippy, with a nice smooth thing. It's basically, instead of having partially hydrogenated food oil, you'll notice a lot of them have palm oil. So if you look at the ingredients in some of your Skippy peanut butters, that kind of thing, you look at it, it'll say that there's palm oil in there. And that basically provides a plant-based, solid triglyceride that will have the same properties. If there's anything else I was going to say about that. I've always wondered if you did the math, because the Crisco, the old-fashioned Crisco, even Crisco, you can still buy Crisco, and if you look on it, it'll have palm oil in there, and I think they got rid of the trans fats out of there. The other thing, a good thing, is this was a pretty common, pretty common in at least North American food supply, was all these trans fats, and it'd be interesting to do the math and say, well, by introducing that technology, we killed this number of people or at least shortened their lives by this amount. There's probably some kind of ugly math involved in that. Here was a product that was really slow to actually change. What is, the icing, the frosting that you get, the pre-made frosting that you put on your cakes and like that, that still had trans fats in it. I was looking like 3 or 4 years ago, and it was still loaded with trans fats. I think they've changed it by now, but yeah, some products were slow to change. I guess if you're buying cake frosting, you're not being a real health-conscious consumer at that point. Okay, that's fats and oils, the story about trans fats. Okay, now we're going to move on to the third one, triacylglycerols. Now what we're going to do is we're going to talk about wax and wax esters. All right, biological waxes. Think about on your body where we've got the ear wax. We've got there's a little bit there's some glands on our skin that excrete a little bit of wax in there. There are different birds have wax that go under their waterfowl have wax that go under their feathers. They have these special wax glands on there. Of course, in plants, your apple, the skin of the apple has a lot of wax around it. So it's this. It basically provides a waterproofing in a sense for whatever tissue it's associated with. Okay, so waxes are mixtures of long chain molecules. Hydrocarbons, so when I talk about like long chain, 20 to 40 carbons long. Long chain fatty acids. And long chain alcohols. Then wax esters are esters between fatty acids and long chain alcohols. I'll give you an example. The spermaceti oil. Remember that stuff in the head of the sperm whale that's in this special organ that's used for echolocating its prey? That is spermaceti oil.
Professor?
Yeah.
I'm sorry, could you, what's A for under waxes?
Here,
Yeah.
hydrocarbons. Let me try redrawing that meter. So spermaceti oil, for example, has 18,1 acid, so it's oleic acid. To a 12O alcohol. This is small enough, let me go ahead and draw this out. So we have our oleic acid. And then we have a 12 carbon alcohol. Like so. And we form a ester between the two. Water comes out. So that would be a wax ester. Another example is jojoba oil. You know, jojoba oil is valued as a cosmetic. It's also as an industrial lubricant. And what it is, a 21 acid with a 22,1 alcohol. I'll tell you a little war story about from the plant biotechnology days, in that there was, again, over in Davis, this is where the Monsanto site was, their expertise was genetically engineering plants to change fat composition, basically. And so one of the projects over there was to take an oilseed plant like canola, and canola normally accumulates a plant oil. It's polyunsaturated plant oil, triglyceride. Basically, genetically engineer it to, instead of making the triglyceride, actually make an ester with the same composition as a jojoba oil. So basically, make a canola plant that would make jojoba oil. And it worked. It's kind of amazing. They first did it in the model systems, and then they actually got it into canola and made it canola. And you know, the amount of jojoba oil in the seed oil was pretty high, but the seed still germinated. It's not like you killed the seeds by doing that, so it was all good. But then this is kind of the way it goes. So the technology was success, but then when you start actually looking at the economics of introducing the technology and what is the real demand for this stuff and what's it going to cost to get it to the regulatory process and all of that, it didn't pencil out. So it was a technical success, but a business non-starter. Well, actually, they started because they did the research, but it ultimately didn't come down. And this is a common problem, basically, in technology. Is sometimes the technology is there, but the intricacies of the business model is such that you can have a technical success, but then you can't figure out a way to make money from it. Another sort of war story with the genetic engineering of plant oils. So detergents, we buy detergents, sodium dodecyl sulfate. Okay, so it's sodium dodecyl sulfate. So it's a 12 carbon chain with a sulfate on the end. It's made from a C12 fatty acid, lauric acid is its name, which is also a component of palm oil. And so the commercial source for when you need to make your detergent, so this is all the detergent in your dishwashing liquid and your laundry detergent, and your shampoo, and all of that, is to take lauric acid and then convert it to this sulfate, basically. Back in the late 70s, early 80s, there was concern about the supply of palm oil to get the lauric acid, that it was being grown in politically unstable parts of the world, and there's potential for there to be a big price increase in the cost of the lauric acid derived from palm oil. So people investigate in a technology to try to make other oil crop plants make the C12 fatty acid. And so again, over at Monsanto over in Davis, again, it was a technical success. They were able to engineer canola plants to, rather than making their normal triglycerides with 16 and 18 carbons long, they would have the 12 carbon long ones in there. So you basically had palm oil-like canola plants. But again, the business situation turned out people started planting palm acres like crazy, particularly in Southeast Asia, and so there was a tremendous increase, and so the price of lauric acid went down, and then it just didn't make sense anymore to have canola, be growing your C12 fatty acid in Canada and the northern U.S. in a canola plant. All right, wax ester. Now we're going to get to our phospholipids. Getting closer to membranes. Well, first we're going to have glycerophospholipids. So as you might expect, phospholipids are lipid molecules that actually take a phosphate, right? But we're going to see that the phosphate, they're associated with different fundamental structures. The first structure are ones that have a glycerol backbone. Then we'll also talk about the sphingolipids, which have sphingosine as a backbone, but we'll get there in just a second. So with glycerophospholipids is we have two fatty acids. Again, we have a glycerol backbone, just like we did with the triglycerides, except we now only get esterified two fatty acids, esterified to glycerol. Plus one polar head group. So we're gonna do the same thing. I'm not gonna draw the actual formation of the ester. We'll just start out with the ester. So we'll have a fatty acid attached here. What's your favorite fatty acid now? Do you have a favorite one? No. Anybody? You have a favorite one?
I don't think so.
Name one. Name one. Shall we? 1, 2.
Let's see, probably the artichoke one, just because I like vegetables.
The what?
The artichoke, the aspartate.
Oh no.
Oh wait, no, that's
Fatty
amino.
acid. Fatty acid.
Sorry.
Did I say amino acid? I meant fatty acid. What do you have for a fatty acid? Somebody give me a fatty acid.
Palmitic.
Palmitic, okay,
Yeah,
good,
nice
yeah,
and easy.
2, 4, 6, 8, 10, 12, 14, 16, okay. Now we'll do linoleic acid. 1, 2, 3, 4, double bond, 1, another double bond. That's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so now we have our 2 fatty acids esterified. But that at this third, a triacylglycerol would have a third one here. But rather than doing that, we're going to put some sort of polar head group. And the most simple one is if we just put a phosphate. So now we have a phosphate ester there. Yeah.
I just had a small clarifying question that I've been noticing. So whenever you draw the double bond on the fatty acids, it's always gonna start at like the 9th carbon? Yeah? Okay.
Yeah, so a lot of the common fatty acids have the double bond between the 9 and the 10 carbons in there. And then the ones that have multiples will tend to have them other. It's not exclusive. There's some that will actually have the double bond in other positions, but it's probably most common that it'll have it in the 9 to 10 position, plus maybe other places too. Okay, so this molecule here is phosphatidic acid. And it's a relatively common glycerophospholipid. It is, among other roles, it is one of the lipids that makes up the phospholipid bilayer of biological membranes. So what we basically have is we have in this area here, we have a nonpolar tail. Then up here, we have a polar head group. So that structure enables the formation of the phospholipid bilayer. So what we'll often see it depicted is something like this, which each one of these is a phospholipid like this, and we talk about when we have a bunch of them, we form a bilayer. Have you guys seen this kind of depiction before? Something like that, right? And so what this gives, this is the polar head group. And then this is then here are the nonpolar tails. So you have to kind of convert this into one of these you have to kind of think in 3 dimensions and squiggle it around a little bit, but that's the idea. Now this is just one of many different phospholipids in here. So the other thing is you can typically coming off this oxygen here is you can start putting a bunch of other stuff on there. So I'll give you one example, is choline. So choline, and I'm going to save a little bit of time, is I'm going to put, just put the R group here. Now we're going to have a quaternary amino group here. With a positive charge here. So we've got to end up with a zwitterion here. So this structure right here is known as choline. This whole molecule is known as phosphatidylcholine. So often the specific polar head group is going to vary among these different molecules. And when we start talking about membranes, we'll see that actually different kinds of membranes are very specific in terms of their, that different membranes will have different phospholipids as compositions in there. So there's some functional significance to this. Here's the other thing, this molecule is known as lecithin. It's a common name. So you'll see this in cosmetics, in shampoos and conditioners and that sort of thing, and in various different, what do you put this when you rub?
Lotion?
Lotions, thanks. Okay. Now one question becomes, where does this stuff come from? Where does this stuff come from? Well, one place where this, like if you're going to put lecithin into your lotion or lecithin into your shampoo, where do you get it? Well, one place you get it is you go to the rendering plant. You know what the rendering plant is? Anybody familiar with the rendering plant? Maybe if you live out towards Rancho Cordova or Alice, that you might know a little bit. That's where they take, some farmer has a cow die in their field and they can't slaughter it in the normal thing. They'll take it to the rendering plant and they basically grind it up and make stuff out of it. So they'll extract high value things out of it like lecithin. That's also where like old restaurant grease goes, and they're pretty efficient in terms of matching their supply with whatever. They also make biodiesel sometimes out of the old restaurant grease and all that sort of stuff. So that's one place. So if your lotion or what have you just says lecithin in it, it probably came from an animal source. Now, a lot of people who buy lotions and that sort of thing are sensitive to that. So sometimes they'll have a vegetable source of lecithin, and that is soy lecithin. And so where that supplies, I'm just kind of giving you a little insight into sort of these industrial processes. So soybean, again, you go back into the Midwest, and soybean is a big business. Corn and soybean, those are the two big businesses. And the business of soybean is you grow the soybeans up and you crush them, and soybeans have mostly protein and lipid in them. And so you crush up the soybeans in there, and then what they actually do is they extract the crushed up soybeans with N-heptane, with just 7-carbon solvent, and that extracts all the oil out and any other lipids that are in, extracts all the oil, and then they boil off the heptane. That leaves you with your oil. That's what your vegetable oil. Vegetable oil, it doesn't come from vegetables. Well, unless you call soybean a vegetable. Vegetable oil is soybean oil. So that's where it is. But they'll take that, and they'll take that extract, and they'll run it through, and they'll purify out the lecithin, because that's a high value product. And so now you have soy lecithin, and they can sell that for a lot more than they can sell just the straight vegetable oil for. All right, so there's a bunch of other, if you if you actually get rid of these methyl groups, the head group becomes known as ethanolamine, and so there's another one called phosphatidylethynolamine. You can actually attach amino acids there. For example, you can attach serine there, and then it'll be phosphatidylserine. So there's a whole bunch of different flavors of these polar head groups. The other thing that we can have is galactolipids. So what do we have? Phospholipids, glycerophospholipids. Then this is sort of, these don't necessarily have phosphates in there, but I'll kind of include them here. We also can have galactolipids. And sulfolipids, in which the polar group has either galactose, a sugar coming off of that at this position, or various different sulfur-containing compounds in there. These are common in chloroplast membranes.
Professor, are you saying those are different types of lecithin? Or what?
No, these are actually other polar head groups that can
Okay.
be, yeah. I'll show you some pictures of these. All right, so so again, here's the overall structure of a glycerophospholipid, right? And the specifically phospholipids, we can have a bunch of stuff, different things down here. Here's some different examples of different head groups. So I mentioned phosphatidylethanolamine. This is a phosphatidylcholine. This amino acid, phosphatidylserine. You put glycerol there, phosphatidylglycerol on there. Then here's some more complex sugar structures that are also phosphorylated that can be on there. Oh, this molecule here is cardiolipin. It has this big complex structure in there, and then it actually can be attached to a second glycerol backbone. So again, there's the derivatives of those can be relatively complex. The formation of bilayers, we talked about that. I thought I might have I don't have a picture of a galactolipid or a sphingolipid in there. All right, so let's see. Let's at least introduce sphingolipids, and then we'll call it a day. So maybe another 10 minutes or so. So I think I'm going to leave this up here. I'm going to leave it up over on the side. To remind ourselves, structurally what's important here is we have this nonpolar tail, and then we have this polar head group. Because these other sphingolipids will actually achieve that same structure, but not using the glycerol backbone. We have the glycerophospholipids, and now number 2 is the sphingolipids. A lot of these are particularly abundant in plasma membranes. You know, there's a lot of different membranes, right? There's plasma membranes, there's the Golgi apparatus, there's the mitochondrial membrane, there's the nuclear membrane, there's vacuolar membrane. There's a lot of different membranes. These sphingolipids are particularly prevalent in the plasma membrane, but also they are prevalent in nerve cells. They're particularly present in nerve cells. Okay, so what's the structure? And the structure is based upon sphingosine. So sphingosine has this structure. I'm gonna start and kind of work back this way. Start with the methyl group. Okay, this molecule is sphingosine. Now I drew it this way where I could have just drawn it as like a straight line, right? But I drew it this way to kind of emphasize the fact that we're going to end up with a structure similar to our glycerophospholipid. All right, now what we're going to do to get another similarity to this is we need a second chain here. So we're going to put a fatty acid at this position, except instead of making an ester like we did over here with the glycerol backbone, we have this nitrogen here. And so we're going to make an amide linkage to a fatty acid at that point. So we're going to end up with and we're going to put a fatty acid here. We'll just do a palmitic acid. 2, 4, 6, 8, 10, 12, 14, 16. And so this molecule that has the sphingosine plus a fatty acid, it equals ceramide. Now, this is a site for attachment of a polar group. And what we'll do is we'll talk about different polar head groups creating different slightly different sphingolipids that are prevalent in different cells of different tissues. So for example, if we have ceramide plus phosphocholine so that's where we would have a phosphate plus the little group that had the quaternary amino group, so that's phosphocholine, serine plus phosphocholine. or phosphoethanolamine. Okay, so what this is sphingomyelin. And this is abundant in Schwann cells, in the myelin sheath. You anatomy experts might have to correct me, but my understanding is surrounding some of the nerve cells is another cell called the Schwann cell that wraps around and around and around there. It's this very extensive plasma membrane, and it's very highly enriched in these sphingolipids, particularly this sphingomyelin. I'll show you a picture of that in just a little bit. Okay, now if we have ceramide plus a glucose or galactose as a polar head group. That equals a cerebroside. And again, these are very, very abundant in the membranes of nervous cells, particularly up in the brain. That's why it gets a name like cerebroside. And then ceramide plus more complex carbohydrates. So this is just a simple sugar, single sugar, plus more complex carbohydrates. You can say more complex sugars. That equals a ganglioside. So what we, so we have a lot of variability, right, in these lipids that end up are going to be making up our membrane bilayer. And an interesting question to ask why. The most simple one was the phosphatidic acid that just had the glycerol backbone plus a phosphate, right? Why do we need all these variations things? And I think it's because that the membranes are really pretty complex, and they have very specific functions and structures, and that require different variations in the properties. It's not just as simple as a simple lipid bilayer, that there are different elements. And what this variety does is basically provides that membrane layer with variations in physical properties that can be adapted for whatever physiological role it might take place. Let me finish up with just a couple of slides here. Reiterate this. Okay, again, here's our sphingosine molecule here. When we add the fatty acid that's now connected via an amide linkage to the sphingosine, we get a ceramide, and then we're going to add a polar head group to get our sphingolipid there. Again, here are examples of different head groups. The sphingomyelin with the phosphocholine, the cerebrosides with glucose, and then these gangliosides have much more complex sugar structures at their head group position. But ultimately, it still gives you that same polar head group with the non-polar tails, whether it's phosphatidylcholine here, the two with the non-polar tails, the polar head group, or whether it's the sphingomyelin here, they have a similar structure, but not exact structure, so they are going to have a little bit different physical properties. Oh, here, this is a micrograph of the myelin sheath. So here's our nerve cell is in the middle. The Schwann cell is this funky shaped cell that basically just is a cell that layers around and around and around and around there, and it has an extensive plasma membrane. And this extensive plasma membrane is full of these sphingomyelin as a component. And it basically provides electrical insulation for the nerve cell, is my understanding. No, there was the galactolipids and sulfolipids in the wrong place, so I just leave that there. Okay, so we'll come back tomorrow and we'll finish up with the lipids. And yeah, I think pretty much what we'll end up doing is finishing up